Hello, welcome to this video. Today we're going to look at this problem. So, an is defined as the square root of 2 plus the square root of 2 plus the square root of 2 plus on and on until the end here ends like this, square root of 2 plus square root of 2, where 2 appears n times. And what we want to show is, I should say, for all n as natural numbers, we have that 1/2 is bigger than 2 minus an divided by 2 minus an minus 1, and that's bigger than 1/4. So I'm going to actually now clear the board and then prove that an always has to be between 0 and 2 for all natural numbers n, and we'll continue on from there. Okay, so let's look at this. So by our definition of what we know about an, we saw that an was the square root of something. An is the square root of 2 plus the square root of 2 plus blah blah blah, all that stuff. And because it's in the square root, we already know that an is bigger than 0. So now we go to the real hard part of this section of the proof, and to show that an is smaller than 2. And I'm going to do that by induction. So let's see. So first of all, we want to get a connection between past terms, between an and an minus 1, so we can actually work with our induction. So if we continue here, an, we get 2 plus that's all the way on to plus the square root of 2 plus the square root of 2. And 2 appears n times, meaning that if we square an, we get rid of this square root, and then when we subtract by 2, so minus 2 plus an squared, we get rid of this 2, and we are left with the exact same looking square root type number, except instead of n amount of 2s, we have an n minus 1 amount of 2s inside this, meaning that by our definition of an, this has to be an minus 1. Because again, it's the same form. Square root of 2 plus the square root of 2 plus on and on till the end. Well, we have n minus 1 2s, that's an minus 1. And we just found that that is an squared minus 2. So that is our connection. Now let's use it in our induction proof. Okay, so now let's see. So the first step of any induction proof is the base case. So we want to show that for n is equal to 1, we do indeed have that an is smaller than 2. So that's really easy because we know the value of a1. Because remember, an is when we have n 2s, so a1 is when we have a single 2. So it's going to start the square root of 2, and then we already used up our 2, and then we cannot add another square root inside. So a1 is square root of 2, which is clearly smaller than 2. So that is the base case. Now let's go to our actual proof. So we're going to assume that this works for a of n minus 1, and then we're going to show that that implies that it also works for an, like any other induction proof. So let's see. We know that an minus 1 is smaller than 2. Well, we're assuming that, but that's our induction hypothesis. And if we add 2, that means that this is instead now smaller than 4. And adding 2 to n minus 1, like we saw, gives us an squared. But now, if an squared is smaller than 4, and because an is a positive number, we know for a fact that an has to be smaller than the square root of 4, which is 2, giving us the end of our induction proof. We started with an minus 1 is smaller than 2, and we quickly got that that implies that an is also smaller than 2. And because our base case works, again, that will mean that for any natural number n, an is smaller than 2. We easily saw earlier that an is also positive or bigger than 0. So an is now between 0 and 2 for every natural number n. Now let's clear the board again and quickly finish off the proof. Alright, so now let's see. So to continue the proof, we actually want to simplify this number, because this fraction, because it looks hard to work with an minus 1, 2 minus, and divided by. I don't want any of that. I just want a simple fraction. And again, we're going to use what we found out the last board, which is an minus 1 is equal to an squared minus 2. So all we simply need to do is to plug an minus 1 in here and see if we can simplify. So the top stays the same, 2 minus an, but the bottom is now 2 minus this. So it's 2 minus an squared and then plus 2. So 2 minus an squared plus 2, which gives you that the fraction is 2 minus an divided by 4 minus an squared. And that fits perfectly, because now we can, by difference of squares and the fact that 4 is just 2 squared, see that we can turn this into a product. This is 2 minus an times 2 plus an. Again, by differences of squares. And then we can see that this cancels, and we also know that this cannot end up as 0, as we saw that an is smaller than 2. So that's also good to see. And we end up with just 1 over 2 plus an. So now we only have to show that this is between a half and a fourth, because we know that this is equal to our original fraction. So if 1/2, so now let's use what we found out last board, that 0 is between an and 2. So we're just gonna do some simple inequality arithmetic. So to get to this fraction, we need to add 2 and take the reciprocal. So if we add 2, we get that 2 is smaller than 2 plus an, which is smaller than 4. And then when we take the reciprocal, because all of these are positive numbers, we don't have to think about it too much. All we need to do is take the reciprocal of each one of these and flip the signs. So we have the reciprocal of 2, which is a half, the reciprocal of 2 plus an, which is this fraction, obviously 1 over 2 plus an, and the reciprocal of 4, which is a fourth. And now, we take the reciprocal of each one, we simply flip the signs, and we got that this fraction is indeed between a fourth and a half. And because this is equal to our original fraction, we can finally deduce that 2 minus an divided by 2 minus an minus 1 is indeed between 1/2, which is smaller than a half, and bigger than a fourth for all natural numbers n. And that's it. If you want more content like this, please subscribe to my channel. I'll be uploading more interesting problems like this in the future. Finally, that's it.